Hi, everybody. So this is problem number 5 from the worksheet. It says something like this: at what fraction of the amplitude? In other words, what is S as a fraction of the amplitude? What position is the mass in when the kinetic energy is equal to 3 times the potential energy? Keep in mind, in a mass spring system, the mass is oscillating back and forth. And at the amplitudes, it has maximum potential energy. And at equilibrium, zero, S equals zero, it has maximum kinetic energy. So at all the other points, it has both. It has some kinetic and some potential. So there are some point, or there's some point or points where this is exactly true, where the kinetic energy is exactly 3 times the potential energy. And that's what we're going to try to solve. So the way we need to start looking at it is we take that total energy equation. It says that the total energy is the sum of the potential and kinetic energies at a given point. So at some point you have all potential, at some point you have all kinetic, but at most points you have a combination of both. So this is how that equation writes out. 1/2 Ka squared is the total energy, because when you stretch the spring, a distance a from equilibrium, that's when you have the most potential or the most total energy in it. And then, oops, that's 1/2 K S squared. This is the potential energy at given point S, any given point S, and this is the kinetic energy at any point as it goes back and forth. So what we want to know specifically is, when is this equal to 3 times that? Or in other words, watch what I do here. Your total energy, of course, your total energy stays the same throughout. Your potential energy is going to be 1/2 Ks squared for whatever S you're at. But we want to know when this is equal to 3 times this. Or in other words, 3 halves Ks squared. That's the key relationship in this problem. When is the kinetic energy equal to 3 times the potential energy? Or in other words, what is S when that is true? So what we simply do is substitute 3 times the potential energy. Potential energy is 1/2 Ks squared. 3 times that is 3 halves Ks squared. We substitute that in for the kinetic energy. What we now have is an equation with things that we can solve for, right? We can solve for S, what S, as a factor of A. Because, you can see what's happening, right? The Ks and the 1/2s are going to cancel out. All right, so let's do that first. Let's divide everything by 1/2. Okay, and you're left with Ka squared equals Ks squared plus 3Ks squared, right? Now we'll combine like terms. Ka squared equals 4Ks squared, right? 1Ks squared plus 3Ks squared equals 4Ks squared. I'm looking at my video right now, and I'm not sure you can read that very well. Maybe it looks better when it's the whole screen. We'll see. What I have here is Ka squared equals 4Ks squared. Of course, I can divide both sides by K, so that cancels out. So I've got A squared equals 4S squared. All right. Now, I need to know what S, as a fraction of A, what is the displacement when this is true? So I'm going to solve that for S. So I'm going to divide both sides by 4. So I get A squared over 4 equals S squared. Now I want to solve that for S. So I've got to take the square root of both sides. So when I take the square root of both sides, I get S equals plus or minus A over 2. Plus or minus, because whenever you take a square root, the answer can be plus or minus. And then the square root of A squared is A, the square root of 4 is 2, plus or minus A over 2. So half the amplitude. Halfway between the amplitude and equilibrium is where this occurs. And the plus or minus means it happens on one side and the other side. So as it's going back and forth, it happens on this side of equilibrium, it happens on this side of equilibrium, and on this side of equilibrium. So that's all the plus or minus. So that's how you would solve problem number 5.